A sky full of stars, 'cause you light up the path. I don't care, go on and tear me apart.
Hello and welcome to this video on phase difference and path difference. Very similar concepts, but it's important we understand the differences. Okay, let's dive right in. Coherent sources, two or more sources which have a constant phase difference. Phase difference, the fraction of a cycle between the oscillations of two particles measured in wavelengths, degrees or radians. Okay, so coherent sources, that means the two waves have the same frequency. Phase difference, so that's the fraction of a cycle. So if we're talking about two sources and they're doing the same thing, then at the same time, the oscillations are the same, the frequency is the same, so we can say that they're coherent. They could be coherent sources if they were doing this, just so long as they're doing it at the same time, with the same timing. That would be coherent. And then the phase difference just tells us the difference between the oscillations of the particles. So if we got two particles and doing this, so they got the same, there's no phase difference, so we say that they're in phase, right? They're doing the same thing. If you've got two particles, one is doing that, one is doing that, but they're doing it at the same time. They're never catching up with each other. So then these ones are completely out of phase. And they have a phase difference of 180 degrees. So they're doing the opposite of what the other one is doing at any given point in time, isn't it? Yeah? Okay, so that's phase difference. Path difference. Path difference is just when we're talking about two sources emitting waves, and let's just say, for example, they're in phase, they're coherent. So when they go to a certain point, I don't know, across the room, we have to recalculate what their phase is, what the phase difference is going to be at that point. And one of those factors that are affecting it is that if one wave has travelled further than the other wave, then it's going to be doing something different than it was at the beginning, because it will have travelled a different distance. If they travel exactly the same distance, then they're going to be doing the same thing as what they were at the start. But if one of the waves has travelled further, then we have to recalculate what that wave is going to be doing at that time. Okay, so let's take a look at this example here to expand on what we just talked about. Okay, so in a ripple tank, two dippers D1 and D2, 6 centimeters apart, produce coherent waves of wavelength 4 centimeters. Is point X a maximum or a minimum? Okay, and we've got a diagram here that explains what that question just said. So dipper 1 is here, dipper 2 is here, and they're producing coherent waves. Now what does that mean? Well, coherent waves we just talked about means that the waves have the same phase difference. So that means the waves are the same frequency. Okay, so they're producing essentially the same waves. That means at point X there's going to be some kind of interference here. We want to know what kind of interference is. So we want to know what kind of phase difference has the path difference caused. Yep. So to do that, we need to work out the distance each wave has travelled to point X. This wave has travelled 8 centimeters to point X. And we don't know how far the waves produced by dipper 2 have travelled to X. So we need to calculate that. And we can see in the example here, they've just used Pythagoras' theorem to calculate the distance of D2 to X. And the answer there that they've got is 10 centimeters. So we know that there's a path difference then of 2 centimeters. D2 has travelled 2 centimeters further than D1. And what does that mean then? Well, since we know that the wavelength is 4 centimeters, the additional 2 centimeters is half a wavelength. So D2, waves from D2 will have gone an extra half a wavelength than waves from D1, which means that when D2 waves arrive at point X, they're a further half a wavelength out of phase than waves from D1. Now, assuming that waves from D1 and D2 were exactly in phase at the start, then when waves from dipper 2 get to point X, they're going to have gone a further half a wavelength. So those waves, now we'll have one that's in phase that's traveled a whole number of wavelengths, and one that's out of phase that's traveled a whole number of half wavelengths. So the result is we're going to have the waves are 180 degrees out of phase, giving destructive interference and a minimum. We had waves being produced by two sources here, and they travel a certain distance to point X. Now, if they're coherent sources, that's important because the frequency is going to be the same and the wavelength is going to be the same. But it doesn't, just being coherent doesn't tell us that the waves are going to be exactly in phase at the start. That also needs to be specified. So we need to know the initial phase difference. Telling us they're coherent doesn't tell us that the initial phase difference is the same. So there's a slight problem with this worked example, but we can expand on that and see what that means here. So this one, two waves from coherent sources meet and interfere. Which row of the table shows the correct type of interference that would occur with the stated phase and path difference? So initially the phase difference is the initial phase difference between the two waves. After travelling a certain distance, what is the phase difference caused by the path difference measured in wavelengths, and what interference can we expect to see? So let's pause the video, see if you can work out the answer. Okay, let's have a go at it then. Okay, so A, initially the waves have a phase difference of 180 degrees. So that means initially they're doing this, they're out of phase by 180 degrees. And then after travelling a certain distance x, they both travelled the same distance essentially, or the same, after travelling a certain distance, they both ended up at the same point as they were initially. So there's no change to the phase difference, so that means they're still 180 degrees out of phase, so we'd expect destructive interference there. Okay, let's have a look at B. Initially the same thing, they're 180 degrees out of phase. Now after travelling a certain distance x, one wave has travelled further by half a wavelength, or it might be that they've travelled 1.5 wavelengths further, or 2.5 wavelengths. It doesn't matter. It just tells us that after travelling a certain distance x, there's a difference between those cycles of half a wavelength. Now, if initially they were 180 degrees, so they were doing this, now with now we've got to consider that there's another phase difference of half a wavelength, so that brings both of them into phase. So now they're doing this. Now we've got constructive interference. So this one is correct. Let's just double check that by looking at C and D. So initially 360 degrees in phase. After travelling a certain distance, there's been no change. Once they've got to that point X, they're still doing the same thing. So still doing this, so that should be constructive. This one, 360 degrees, doing the same thing. After travelling a certain distance X, there's interference, so it's been changed by half a wavelength, it's been changed by 180 degrees, so now they're doing the opposite thing, they're doing this, so this should be destructive interference. Okay, so the answer is B there. Okay, thank you.
Your sky.